Okay, all right. So in these few talks, we are going to talk about basically the fluid mechanics. Just give you a very bird's eye view of the fluid mechanics, so to speak. So first, we need to know that, for hacking a measurement course, you need to know that why do we need to take measurements? So the reason that we need to take measurements is as follows, because we want to know that how, for example, a fluid behaves. And once we know that, this can enable us to design new things, for example, a gas turbine combustor, or even a microfluidic device, anything and everything. We can actually, if you know fluid mechanics and if you know what you can kind of measure, this is what you are going to get. So if you look at in general the fluid mechanics, so there are, what are the properties? So there will be first material properties. Okay? So material properties can be like many things, like for example mass, viscosity, okay, thermal conductivity, which is K, and of course molecular diffusivity. These are all material properties. Okay, and bulk modules and surface tension, very important in the case of droplets, for example. And then coefficient of thermal expansion, index of refraction, which is N, and fluorescence, and a specific heat under constant pressure, so long and so forth. Similarly, you have the kinematic properties. Okay, so the kinematic properties like are, for example, volume flow rate, okay, displacement, acceleration, velocity, acceleration, okay, angular displacement or angular momentum, angular momentum, angular position, vorticity. Vorticity is very important, and so long and so forth. So there are lots of kinematic properties. Then, of course, you have dynamic properties. Though we say properties, these are actually dependent on the flow. These are not something that you know a priori. Okay, so dynamic properties are force, then you have pressure, then you have stress, then you have torque. Okay, then of course, so these are things that are applied onto the system. Then of course you have thermodynamic properties. The thermodynamic properties, look at it. So there are plenty of thermodynamic properties which you already know. Internal energy is one of them. Internal energy, enthalpy, okay, heat flux, work, energy, entropy, and temperature. So when you do fluid mechanics, okay, you are particularly interested in knowing parameters like velocity. And once you know velocity, you can find out things like acceleration and vorticity. You are interested in finding force, pressure, stress, torque. These are things that you can measure. And similarly, you want to measure, for example, temperature. This is a very important quantity in which a lot of diagnostic methods are dedicated to this, finding out the temperature. Similarly, these are kind of measured in different ways, not using the methods that we are going to talk about. So we are going to focus on measuring these parameters, for example. Okay? And we are going to therefore use techniques like optics, lasers, okay, and stuff like that to measure these. So what we are trying to say is that the measurement techniques, I have to put it, for doing those things, okay, are kind of, we would have point measurements, we'll have field measurements, and we will have, probe based measurements. Okay, probe based, these are intrusive. Okay. So these are the measurement techniques that we are going to use, and almost invariably all of them will have lasers, light sources, okay, optics, and you will have cameras, okay, photo multipliers, okay, and all these. So you need to have a very good understanding of optics, okay, and laser physics a little bit, okay, and of course image processing, so long and so forth. And each specific technique has got certain uniqueness that are attached with them. All right. So this is the kind of things that we have. Now let's do a quick recap or quick understanding of the different flow velocities, because we know that that's a very important quantity, so to say. So the flow velocity, okay, and this is a vector. It has basically three directions: I equal to 1, 2, 3, and then you have xi being the direction. So you can also write it as xyz as well. It doesn't matter. So this is basically telling you that how the particle, for example, if you look at a typical, Lagrangian situation, like, x2, this is say x3, something like that. Okay, and you have a particle trajectory like this. So initially, this vector, this position vector was this, then the position vector was this at some other point. Okay, so you have this change so the flow velocity. This is at two different times, or ti, and some later time. So basically, your velocity is given as dxi by dt, which is basically this is high school. Okay, so this is the velocity at any particular direction. So the position vectors, and then you basically do a vector fraction. So one approach is to identify the initial coordinates of a fluid, okay, and namely the coordinates and the position of the fluid at the origin of time. So this is say at x0i at time t equal to 0, and then there is a final position, okay, which is at a later instant of time, right? So by doing this, you can find out then the velocity, which is basically nothing but the slope of the path. So this approach, okay, the velocity field therefore can be specified as a function of these two variables, is basically vi is equal to vi x0i comma t. Okay, this approach is called the material or the Lagrangian description of the motion. So this is Lagrangian. All right, this is the Lagrangian description of the motion. It basically involves the tagging individual fluid elements, and this is not practical because you have to calculate the trajectory of almost thousands of particles. So it is much better to have to express the velocity field in terms of a fixed position with respect to the coordinate system and of course time. This approach is called the spatial or the Eulerian description. Spatial or Eulerian description is basically you have a fixed coordinate system. Okay, so it's a fixed position with respect to a coordinate system. Coordinate system, okay, and then you kind of the velocity therefore here, if I have to differentiate, is given as a function of xi comma t. It is nevertheless understood that at all positions and for all times, the definition of flow velocity is unique. So therefore, vi x0i comma t is basically is equal to ui xi comma t. Okay. So the following the Lagrangian description, in the Lagrangian description, and this is basic fluid mechanics. In the Lagrangian description, the acceleration, AI, is given as dvi by dt, the rate of change of velocity in that particular direction. But in an Eulerian description, when you go to an Eulerian or a spatial description, all right, this is a little bit different. Change the color, and as we write this, so here the AI is basically equal to dui by capital U, so t plus u1, okay, ui dx1 plus u2 ui x2 plus u3 by dx. Okay, so the first term on the right hand side, this is called a local acceleration. Okay, and the remaining terms are called, basically these terms are basically called the convective acceleration. All right, so local acceleration versus convective acceleration. So right hand side of equation, so this entire thing, whatever you see on the right hand side, this is called the material derivative. Okay, or the substantial derivative of ui. Okay, and it is usually designated as ui by dt, substantial derivative. So that includes the local acceleration and the convective acceleration, right? So similarly, fluid deformation under stress, for example, stress, okay, is described by the rate of deformation tensor, rate deformation tensor, and that is given as, ij equal to half dxj plus uj by dxi. This is a cross derivative, remember, where I is equal to 1, 2, 3. Okay, so this is what we call the rate of strain or the rate of deformation tensor. All right, so this is also something that perhaps you know. Okay, so similarly, now that we know these two, this is important, and the velocity description is given by a field, and the rate of deformation tensor is given like that. Now, of course, just by doing this, you do not have everything at your disposal. You need some analytical description of the flow. So what are the analytical descriptions of the flow? So this the physical relationships between the flow variables are represented by analytical expressions, which constitutes algebraic differential, integral. It can be integro differential equations also, and there are a certain empirical relationships that also goes along with it. Okay, so they are based on the conservation principles. So how many conservation principles are there? There is conservation of mass, there is conservation of momentum, and then there are the conservation of energy. Okay, so when you are applying for a closed fluid system, these principles can give rise to a set of integral relationships. We also have a differential relationships, which we can represent it as well. But however, it is, if you apply it to a fixed control volume, this is once again a part of a full-fledged fluid dynamics course, but I'm just giving you, a heads up. So the conservation of mass, okay, the conservation of mass, for example. So the concept or the continuity equation, as we call it, so this is d by dt, it's a rho dv integrated over v, plus this is over an area, rho v dot dA is equal to 0. Because this is the continuity equation. This is basically the density of the fluid. V is basically the velocity vector. Yeah, and this is the control volume. Okay, and A is the surface area of the control volume, area of surface of the control volume. Okay, so this is all standard. Okay, and for a non-reacting multi-component flow, you can have similar equations expressing the species. And remember, in combustion dynamics or in combustion diagnostics, that is also an important parameter. So this is the mass conservation. Similarly, you have a momentum conservation as well. So the momentum conservation is basically nothing but Newton's second law. Second law. So if it is given as F, let's write it down properly. Volume V O volume plus integrated A rho V bar, where F is the net force, net external force. Because Newton's law, remember, it is F is equal to ma. F is the net external force acting on the control volume. Okay. So it is F equal to ma. Essentially, this is F equal to ma. So that is the whole thing. Okay. So then, of course, you have the energy, which is basically the first law of thermodynamics. So basically, conservation of energy. Okay. So conservation of energy, when you look at it, so conservation of energy is like Q dot minus W dot. That is, and then you have the terms inside. So this is again over volume, Q plus half V squared plus Z rho into dV plus 1 over A Q plus E by rho plus half square Z rho V A. All right. So Q is basically the rate of heat transfer. Okay. And W dot is equal to what we call the mechanical power produced. Okay. Then there are, and shear stresses acting. This is not just mechanical power, shear stresses also, but not normal stresses. Shear stresses acting on boundary. But not normal stresses. Okay. Right. Then, of course, P is the pressure, P is the pressure, Z is the upward vertical axis, G is the acceleration due to gravity. I think these things are kind of well known. Then you have the second law of thermodynamics, second law of thermodynamics, which is, if I write it properly, okay, S rho volume us. This is kind of an inequality kind of a law. So rho greater than equal to 1 over the volume 1 over T Q dot by A. Okay, so S is a specific entropy, okay, and T is the temperature, absolute temperature, the temperature and the absolute state. Okay, all right. So by letting this control volume vanish towards a point, you convert these equations into a differential forms, which you will see what they are. Okay, and of course there are other conditions, like for example, if you have a solid boundary, okay, this is like a wall, for example, then you have the no penetration and no slip. The no slip and no penetration. These are additional clauses that you kind of incorporate, conditions, which basically tells you that the relative velocity normal to the contact surface actually vanishes. And no slip says that you cannot have relative velocity tangential to the contact surface. Now in two-phase flows, you have certain additional things that comes into the picture. So if you have an interface like this is an interface, okay? So you have the delta P across the interface, okay, is related to the surface tension. And so in dimensions, this is basically the two radius of curvatures, the principal radii of curvatures. So across a plane interface, if this is a plane, then delta P goes to 0. Okay, but in a curved interface, when the interface is curved, then these two factors clicks in. Sometimes they can be equal as well. So in that case, when they are equal, it is 2 sigma by r. Okay, so in two-phase flows, this is a customary thing that you do, and then you see that for a fluid, for a flow near a wall, this is the other things that you do. Okay, so there are other types of flows which basically requires additional principles, like for example law of chemical reaction for reactive flows. These are supplementary things that you need to be added for reactive flows. Okay, and then there is magnetohydrodynamics. Dynamics for electrically conducting fluids. For electrically conducting fluids. Okay, in magnetic fields. All right. So among the common types of other types of common types of empirical relationships now. Relationships, okay. So there will be the equation of state. Okay. So for example, for the perfect gas, this is P by rho is equal to RT for perfect gas. There can be other types also. Okay. Then there is a stress and strain constitutive relationship. Relationships, for example, when we say Newtonian, one common example is that we say some fluids to be Newtonian, and some fluids we say non-Newtonian. So that is basically the relationship between stress and strain. Okay, so Newtonian fluid is easy, most common. And then of course you have turbulence. There are turbulence models also. Remember, the turbulence models are models. So they are turbulence models, which is basically mostly they are statistical, okay, properties of the turbulent flow. Okay, so like K epsilon, all those stuff. So so there are, okay, the choice of your analytical approach can be dependent on the type of fluid problem that one is dealing with. So these types of fluid problems can be varieties, and that is what we are going to see in the next lecture, that what are the types of, types of approaches to describe fluid motion. The approaches to describe fluid motion. And, for all of them, measurements are necessary. Okay, right from turbulent flow to all the way up to complex fluids or droplets or things which has interfaces everywhere. This is the most common thing that you can think of. All right. In the next class, we will look into the approaches of the fluid flow that we can encounter in different applications. Okay.